Hi, my name is Jessica Lee, and this is a pre-recorded presentation for the 2021 meeting of the Cognitive Science Society. So I'm interested in this question of how do we generalize associations that we learn in the world? So my research sits at the intersection of two quite different research traditions. So the first is associative learning. So in associative learning, generalization is conceived of as conditioned behavior that is elicited automatically on the basis of generalized associative strength. So here the idea is that stimuli come to control our behavior. So generalization behavior is very much stimulus driven. On the other hand, we have generalization in property induction, and here generalization is conceived of as an uncertain inductive inference made on the basis of limited evidence. And here we really emphasize the role of individual differences, prior knowledge, and the assumptions that people bring to the task about how the evidence is sampled. So my research is really trying to, marry together insights from these two research traditions to understand how humans generalize associative learning. Okay, so a lot of the work that I'm going to be presenting really stemmed from this phenomenon called peak shift. So I'll explain what that is first. So in associative learning, we can administer what's called single cue training. So this is really simple. We just present a single stimulus, CS+, and participants learn that the CS+ predicts some outcome. So the stimuli that we use in our experiments are usually quite simple. So they're just colored shapes like this aqua rectangle here. And then after that single cue training, we administer a generalization test. So we vary a dimension of the CS+. So in our experiments, it's typically the color of the CS, ranging between green and blue. And we get participants to predict how likely they think the outcome would be for all these other stimuli. So when we plot the responses along the dimension, we get a generalization gradient that looks like this. So a kind of symmetrical peaked gradient with the highest predictions for the outcome at the value of the trained CS+. Okay, so for that familiar stimulus. Okay. Now, if instead of single cue training, we administer what's called differential training, so here we have a CS+ that leads to the outcome, but also a CS- that leads to no outcome. And hopefully you'll be able to see here, but the CS+ and CS- look very similar, but the CS+ is slightly bluer and the CS- is slightly greener. So after this differential training, if we then administer the same generalization test, we sometimes get a gradient that looks like this. So the peak of the gradient can shift from the CS+ to a novel stimulus here in the direction away from the CS-. So this is what we call the peak shift effect. Okay, so peak shift has been demonstrated a number of times in animals, but it is relatively more elusive in humans. However, when it is found in humans, it is typically explained in associative terms. So associative models can explain peak shift using quite simple mechanisms like associative excitation and inhibition, maybe in combination with error prediction. But critically, they're able to predict peak shift without having to appeal to any abstract relationships between stimuli. So these models don't represent any concepts like bluer than or greener than, but they can still predict peak shift. So recently, we've published an alternative explanation of peak shift based on the idea of individual differences in the rules that participants derive. So this account goes like this. So we assume that during differential training, there are two different things that participants might learn. So one group of participants might learn something like this. So the more similar the color to aqua or some stimulus feature of the CS+, the higher the likelihood of the outcome. And we can call this a similarity generalization rule or a similarity strategy, whatever you want to call it. And another group of participants might learn something like this. So the bluer the stimulus, the higher the likelihood of the outcome. So here we can refer to this as a relational generalization rule or relational strategy because it concerns the relational difference between the CS+ and the CS-. So if there are individual differences and some participants learn this and some participants learn that, we might expect to see different generalization gradients in these two subgroups. And they might look like this. So we might expect to see a symmetrical and peaked gradient in the similarity subgroup, but this kind of more monotonic sigmoidal function in the relational group. And the key point here is that if you average the two, you get a peak shift at the aggregate. So we set out to test whether this could potentially account for peak shift, and to cut a long story short, that's basically what we found. So we found an overall peak shift, and when we divided participants into these similarity and relational groups based on self-report, we got gradients that were distinct and consistent with their reported rule. Okay, however, if you have a keen eye, you might have noticed that the gradients that we observed in our rule subgroups, they weren't as clearly differentiated as what we might expect if participants were deriving and using only a single rule. So this led us to think, well, okay, what if people are actually using multiple rules when they generalize? So to kind of explore this question, we ran an experiment just to see whether participants actually report believing in both rules after differential training. So in this experiment, we ran 100 participants online. So we administered differential training with partial reinforcement of the Cs+. So this is just typically what we always do in our experiments. And then we administered a standard generalization test. So we presented these stimuli ranging between green and blue in randomized order, and we got participants to predict how likely they thought the outcome would be for each of these stimuli. We then administered our standard forced choice question. So we present participants with these similarity and relational options, and we get participants to just choose which one they think is most true. But the novel feature of this experiment was that after that, we then assessed participants' beliefs in each of the similarity and relational rules. And we didn't constrain these, so participants could actually give maximal ratings for both similarity and relational options. Okay, so these are the data from the rule beliefs question. So we did get a negative correlation between the beliefs. So participants tended to have higher belief in one rule than the other. However, you can also see here that participants actually do have a moderate to high amount of belief in both rules. So we now have evidence that participants believe in both rules after differential training. So the next question was, well, do participants actually use both rules in their generalization? And then if they do use both rules, how do the rules interact? So how do participants combine information from these two rules in order to determine their performance? So to answer these questions, we came up with a mixture of experts framework. So in this framework, we assume that there are two experts, so a similarity expert and a relational expert. And then we also introduced a guessing expert. So we then needed to define how each of these experts generalized. So for the similarity expert, we chose a Gaussian function with 3 parameters, so a mean, standard deviation, and height. So it would look something like this. For the relational expert, we chose a logistic function, which also has 3 parameters, so the location, scale, and maximum, which would look something like this. And for the guessing expert, we just said that the guessing expert responded at 50, and that's because in our previous experiments, we've observed that when people are uncertain, they just respond at 50, which is the midpoint of the scale. Okay, now in order to determine how the experts were weighted in the model, we actually weighted the experts using participants' empirical belief ratings. So the similarity expert was weighted by S, which was whatever rating participants had given to the similarity rule in the experiment, and the same for the relational expert, which is weighted by R. We then calculate the weighting for the guessing expert using this equation here, and this just ensured that participants would be treated as guessing a lot if they had low belief ratings in either expert, and if participants had absolute belief in either expert, then they didn't guess at all. And then we normalized each of these weights so that they added to 1 for each participant. Okay, so to answer the questions that we were interested in, we compared 3 different models. So the first was a single expert model. So here we assumed that each participant generalized exclusively according to either the similarity or the relational expert. So here we just used participants' response on the forced choice question in order to determine which expert that was. And then we compared that to two multiple expert models. So the first assumed that generalization was determined by the weighted average between the three experts. And the second assumed that generalization was determined according to a probabilistic choice between the experts. And the same expert weights were entered into both of these multiple expert models. So we fit the models in STAN using calibrated priors, and these models were hierarchical as well. And we estimated each of these parameters, the 3 parameters for the Gaussian function and the 3 parameters for the logistic function in the model. And then for model comparison, we calculated WAICs. Okay, so just to give you an idea of what these 3 models are doing, I'm going to show you the posterior predictives just for a single participant's gradient. So the black line here is generalization data from just a single participant. So you can see here for the single expert model, it's really constrained because it can only generalize according to one of the experts. In this case, it's the relational expert. So it's not really doing a good job of capturing this particular participant's data well. The weighted average model does a little bit better, but you can see here that the probabilistic choice model is doing a much better job than the other two at kind of capturing this particular gradient. So I guess in one sense that's not surprising because the probabilistic choice model has a bit more flexibility because it can sample from those multiple experts. However, when we calculated the WAICs, we found that the choice model actually had the lowest WAIC. So this means that that model is the most accurate at predicting the data, even after accounting for model complexity. So to answer our questions from before, so do people use both rules? It appears that they do because the model that won was the one which incorporated multiple experts, and the single expert model really didn't do that well in terms of predictive accuracy. So how do the rules interact? The probabilistic choice model won over the weighted average model. So it appears that participants sample between experts on each trial when they generalize. Okay, so just to summarize, so we've provided evidence that participants derive and use multiple rules when generalizing learned associations, and that participants are more likely to integrate the rules by sampling between them on a particular trial rather than averaging. We presented a novel mixture of experts framework in the context of an associative learning task, and what we found is that participants switch between rules from trial to trial. And this is similar to the concept of knowledge partitioning, which arises when participants represent distinct parcels of knowledge and sample between them in their inductive inferences. And our model is conceptually similar to the POL model, which describes how people perform in function learning tasks. So it appears that generalization in associative learning exhibits similar characteristics to that in other cognitive domains. So things like sampling effects appear to be relevant to associative learning as well. And then finally, just to bring this all back to where we started with peak shift. So we've previously shown that at the group level, peak shift can be explained by averaging between relational and similarity subgroups. But now what we've shown is that at the individual level, participants might actually be switching between relational and similarity experts. So what this means is that it might be very difficult for us to actually find peak shift at the individual level, and that kind of corresponds with what I've seen in the data, in that there's a very high amount of variability in the individual gradients, even when we get peak shift at the aggregate. So perhaps this can help explain why peak shift is so elusive in humans. Okay, thanks.